Dear students, welcome and thank you for tuning in to this video with me, Dr. Loay Al-Zube. We're still discussing kinematics of a particle moving on a curved line in the statics and dynamics course. In this video, I'm going to talk about the velocity. And so velocity represents the rate of change in the position of a particle. And we talked about position of a particle in 3 dimensions in the previous video. And now we would like to see how can we identify the velocity. So if you have a particle that is moving on a curved path, we said that in the previous video that we need to identify a reference point. And from that reference point, we need also to identify the point where the particle is at a specific time point on the position, function or the curve of the line, the path that the particle is following, and that's going to give us the r, the position vector r. And to find the velocity, actually, we have multiple definitions. We will look at the average velocity of the particle during the time increment of delta t, and which is the change in r divided by delta t. Also, if we assume that delta t is very small, so we can find the instantaneous velocity, and that is the derivative of dr over dt, assuming that r is a function of time. And remember, r is going to be something like this. R is going to be x of t I plus y of t j plus z of t k. So you will be able to derive each component with respect to time, and then you will get the velocity. And the velocity vector is always tangential to the path of the motion. And that's another important component we need to keep in mind. The magnitude of the velocity is called speed. And similar to the position vector and the magnitude of the position vector, since the arc length is approaching delta t, so delta h is approach the magnitude of delta r as t goes to 0. So the speed can be obtained by the derivatives, and if you have the velocity as a vector, you can find the magnitude of the velocity as the square root of the x component square plus the y component square plus the z component square. And that's how you get your speed, actually. So I hope this is a good introduction or representation of the, so this is my r of the velocity. Now, if we want to look at the acceleration, that's another important concept, an important quantity to identify in kinematics. However, we're going to introduce a new term in looking at the acceleration of a particle moving on a path. So, quick reminder: acceleration represents the rate of change in the velocity of a particle. And if a particle velocity change from v to v bar, which is v final, over interval delta t, the average acceleration will be the change of velocity divided by the change of time. And then if we assume that delta t is going to a small, infinitesimal small quantity, the acceleration would be the derivative of the velocity with respect to time, or the second derivative of the position with respect to time. So this is how we get the values of acceleration. Now, we would like to talk about a little bit more about the direction of acceleration, because that's an important concept as well. So if you look at our path or particle moving on a path, we said that the velocity will always be tangential to the path, and that's your v initial, and this is your v final. So after a specific delta t, we move from this point to that point, and our velocity change from v to v bar. If you would like to find actually the acceleration, which is the rate of change of the velocity, we will take the two vectors, and we will move them in such a way that they are going to be starting from the same point. So I will create another origin, which is O bar, and then I will draw the velocity vector for initial velocity vector and the final velocity vector, and then we will have the delta v. This is called hodograph representation, actually, and the direction of the change of velocity is the direction of the acceleration. So keep in mind, this is how we do this. You have two velocity vectors, you take them away, you put them to start from a new origin, and the difference between them is the direction of your acceleration. And this is a plot of the locus of points of the velocities, and it's defined by the arrowhead of the velocity vectors, and it's called hodograph. And keep in mind, again, the acceleration vector is tangent to the hodograph, but not in general tangent to the path function. And we have a special case in which that if you're looking at a circle, right? So if we are studying a movement of a particle on a circle, your acceleration will always be toward the center. But this is not the case because we will be having such movements. So our acceleration is actually going to be not to the center, the direction of the acceleration. And this could be identified only using the hodograph, which I explained to you before. I hope that was helpful in introducing and talking. There is a lot of information that before about velocity and acceleration, but we introduced a new concept, which is the hodograph, and how to identify the direction of the acceleration of a particle moving on a curved path. Thank you for watching. Until the next video, in which we will be more on how to calculate the velocity and position velocity and acceleration, and how to relate it to the rectilinear coordinates. Thank you for watching. Until the next video. Bye.